Okay guys, back at you with another calculus concepts review. We've made our way to chapter 5, so let's take a look at what we're looking at here. This is a lot of points of discontinuity, a lot of just the definitions of what these different things mean when we talk about them in calculus, and you'll see what I'm talking about. So you're introduced to this really kind of a strange function here. It says here it would be difficult to describe algebraically, and I would tend to agree. That's going to be a heck of a function. It looks like it'd be a piecewise function, but that's neither here nor there. The first thing to do is describe where are there any zeros for f. Now remember, this is the function for f. So zeros for f would be, let's see, right over here at A. Yeah, here at A, over here that looks like at C, over here at G, and over there at K. All of those places, the graph of f intersects with the x-axis, so that produces a 0. Next part, are there any points of discontinuity? Well, discontinuity is a place where if you were attempting to draw this with a straight line, you would be forced to pick up your pencil or draw a circle or something like that. And it looks like right here, this is our only point of discontinuity. There is a jump here, a break, and our point of discontinuity, therefore, would happen when x equals h. Are there any points where f prime does not exist? F prime isn't going to exist. Well, first of all, it's not going to exist at our discontinuity. Secondly, it's not going to exist when the slope from the left and the slope from the right don't agree. Over here at this point, the slope from the left is negative and the slope from the right is positive. You can call that a corner or a cusp if you like. Here's another place where the slope from the left and the slope from the right do not agree. Here's another place. Are there any places where the tangent line would be vertical? And I'm not seeing any, but that's another place where the derivative doesn't exist because the slope doesn't exist. A vertical tangent line means the slope does not exist. So what do we have? B, H, I, and J. D, are there any points where the derivative is equal to 0? Okay, so we're looking at places where we would draw a horizontal tangent line. I see one right here, definitely. Right over here, right down here. And then the next thing is this whole piece right here is horizontal. So the derivative would be 0 all the way from H to I. And then I'm also having a little bit of trouble of deciding, how about here at D? Does that look like a place where the tangent line is horizontal? It kind of does, right? So these are our places where we got f prime equal to 0. So far this has been kind of fun actually. Next part here, critical points. Critical points are any places where the derivative is either undefined or the derivative is equal to 0. So it's kind of a combination of C and D. Here's a place where the derivative doesn't exist. Here's a place where the derivative is equal to 0. 0. Here's a place where the derivative doesn't exist. Over here, that would be a critical point. And down over here, that's a critical point here and here. Now, we wouldn't call this a critical point because that's actually an interval. So that's not a critical point. Yeah, so let's just write those down now. A lot of calculus students mix up the definition of a critical point. A critical point is not a place where you have a relative maximum or a minimum. It's just a place where the derivative tells you something about the curve. Oftentimes, that means that you have a relative minimum or a relative maximum, but not always. Are there any critical points that are not stationary points? Well, it looks to me like the only stationary point that we get is right here at D. Everything else here should be a critical point that is not stationary. Okay, so it's almost the same list. How about this next one? Intervals of increase and decrease. We'll take care of these two together. Intervals of decrease, well, here the graph of f is decreasing. Here the graph of f is decreasing. There's decreasing, and there's decreasing. Now, most of the other intervals are increasing. I'm going to handle D a little bit strangely because at D, the graph is neither increasing nor decreasing. So depending on how, you think about intervals of increase or decrease, whether or not a slope of 0 is included, really depends on what school of calculus you're coming from. As far as the AP test is concerned, they really don't care if you call that part of the interval or not part of the interval. They'll read you both ways and mark you correct both ways. So let's go ahead and write these down, intervals of increase and decrease. Next we have relative maxima, and I assume that also means we have relative minima. So relative minima, relative maximum, of course that's the highest place on a curve where all the points to the left and to the right, well, for a maximum, it's going to be all the points to the left and all the points to the right are lower than that point. So let's look for relative maxima and relative minimum. Here's a maximum. Here's another maximum. Notice that here it forms a peak. This is not a peak, so that's not a relative maximum. Relative minimum, minima, here's one, there's one, and there's one. So we get 2 minimum and 2 maximum. Okay, so what about absolute maximum and absolute minimum? So we're looking at places which are going to be the highest point, and as I'm looking at this, you might want to call this point right here at F. You might want to call that a relative or absolute maximum. But if you take a look over here, this graph is always increasing. So eventually it will surpass whatever the height is over here. So I don't believe there are any absolute maximum. None. What about relative or absolute minimum? You might want to say here, I don't know if this looks even with this one or not. It really depends on what you're thinking or the way you look at it. But neither of those are the absolute minimum, because if you take a look at this part right here, at the asymptote, this curve keeps on decreasing to negative infinity. So really there's no absolute minimum either. Okay, we're going to be moving on. This is going to make me nervous because I'm going to have to scroll up and down for this. But if you take a look, are there any horizontal asymptotes? And I just kind of said that on the left end behavior, this is always going to increase. And that's the way it looks to me anyways. But the right end behavior, this does not look like it's always going to increase. Notice how just perceptibly the rate of increase is decreasing. So this looks like it's going to have a horizontal, or what do you call that? A horizontal asymptote there. So how does this question ask? Find equations of any horizontal asymptotes. So I'm saying that at y equals 0, that looks like a horizontal asymptote to me. I believe the next one is for a vertical asymptote. Yes, it is. And over here at h, although it's true that from the right side it's not an asymptote, it is an asymptote from the left side. So that does make it a horizontal asymptote. It's just a one-sided horizontal asymptote. So at x equals, what was that, h? X equals h. Moving on. Find the x-coordinate of any discontinuities for f prime. So those are places where the derivative will not exist. Where does the derivative not exist? Here, here at h, here, and here. Okay. At all those places, there's either a curve or an asymptote or a break. So at those 4 places, the derivative does not exist. And now we get a little bit tricky because they're asking for a critical point in f prime. So a critical point in f prime is where f double prime is either 0 or undefined. So f double prime is 0 or undefined at any of those places where there is a point of inflection for sure. So let's take a look. Are there any places where we get points of inflection or where concavity changes? Over here, we have concave down, and then to the right we have concave up. So here's a point of inflection. So we have concave down, concave down, concave down, and then all of a sudden we become concave up. So here's another place where concavity changes. Concave up, and then concave down over here. There's another place where concavity changes. Concave down, concave down, concave down. Okay. Over here, there is no concavity at all here. Okay. Not changing from concave up to concave down because these are straight line segments. Second derivative is equal to 0 for all of these. Over here, now we've got concave down, right till we get to right about here, and I think that's L. Concave down, and then it's concave up. And then I don't know if you noticed it or not, we're concave up, and then over here at N, we become concave down again. And that's necessary. That's one of the tells for me to say that this is actually a horizontal asymptote. So here we go. B, D, E, L, and N. Those are the places where the second derivative, where the first derivative has a critical point. All right, so the next thing here is to sketch f prime on the same graph. And wow, that's a little bit on the difficult side. Let's see what we can do. So from negative infinity to b, the slope is negative and it's getting more negative. So we're looking at a piece here. Maybe I'll do this in, yeah, why not? Let's do it in red. So we have a slope that's negative, and it's getting more negative. Now, once we get to B, something weird happens because now the slope all of a sudden becomes positive, and it's really positive. It's not, a slope of 0. So it jumps all the way from this negative point all the way to some positive point up over here. So what happens is the slope gets less and less positive. And when we get to D, the slope is 0. So here we go. Slope of D, and then at D we get a slope of 0. And then it gets more steep until we get to E. And then at E, the slope starts to get less steep. And when we get to F, we get a slope of 0. So here at F, we get a slope of 0. Here at E, we are at the most positive slope. So we're going to come up and come down again like that. Okay. Now at E, starting at F, the slope is negative and gets more and more and more negative. So it just keeps on going down, 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 down. All right, so that's that first part. Here from H to I, that slope is 0. So we can draw that as 0. From I to j, the slope is some negative number. I don't know what it is. Let's pretend that it's, I don't know, right about here. That's a negative slope, and it's a constant negative slope, so that's a horizontal line. Starting from j to k, we have a positive slope, and it's getting closer to 0. I don't know what the slope is here. It looks like maybe a slope of 1. But the slope decreases until we get to k, and at k, we already said that that's a horizontal tangent line. So at k, we have a slope of 0. Now over here at L, we have the most negative slope. So yeah, the most negative slope here. At M, the slope is 0 again. And then at N, from here on out, the slope stays 0, or the slope stays positive. And it gets close to 0 like that. Okay. So I don't know how convincing that was. That's my interpretation. And that kind of ends today's 5.1 concepts review. Went on a little longer than I thought it would, actually, by about 5 minutes or so. But that's it. All right. So have yourself a good day, and we'll see you next time.